All right. Thanks, everybody, for coming in. Thanks for the introduction. And again, thanks to TNG for inviting us here for the presentation, and especially for TNG as being our sponsor. That's the whole reason we're actually here. It's one of the reasons we actually went to California for the first competition. They were the first ones to give us some money to fly over. So we're really grateful for that support. Anyways, but we're here to talk about the competition. And yeah, as you see on the picture, it's a small section of the tube that we are going to talk about. And our team is called the WARR Hyperloop. And what the hell means WARR? It's our student group that we're working in. It's German for Wissenschaftliche Arbeitsgemeinschaft für Raketentechnik und Raumfahrt. So in English would be Scientific Workgroup for Rocketry and Spaceflight. And it's a student group since 1962. They have launched the first hybrid rocket, so like solid rocket fuel and liquid oxidizer in 1974. And since then, there have been multiple student groups. Some are building rockets, some are building CubeSats, some are building space elevators, and some are talking about interstellar spaceflight, and others are building Hyperloops. So let's talk about the Hyperloop. I don't know if anybody of you heard or who's familiar with the Hyperloop. Maybe if I can get a hand count. Great, awesome. Thank you. So I can skip that a little bit. Of course, the Hyperloop, the vision, make transport faster, the same story as always. Get from Munich to Berlin in 35 minutes. That would be one deal, right? Connect cities, make everything smaller. The Hyperloop concept itself is basically you take a train that you have, let it levitate in some kind of way to remove surface friction, and evacuate the tube to remove aerodynamic drag. Right? That's the simple idea. It was proposed by Elon Musk, the Silicon Valley figure from SpaceX and Tesla in 2013, and he published some white paper called the Alpha Study, where he talked about a very specific concept of the Hyperloop that he envisioned, which used air bearings. So a little buffer of air that you're levitating on, and a compressor at the front to suck in the air, the remaining air in the tube, compress it, and use it as your air bearing. Now, if you want to look at it in more detail, it's a small picture from that very study. You have in the front the compressor that takes the remaining air in the tube, because you're not going to use a very high vacuum in the tube. Like a very high vacuum is pretty inefficient, is pretty expensive to maintain. So you don't want to use a low, let's call it a low vacuum, something around like 1 millibar of pressure, right? So in that tube, and there's still some air left, and you want to make the tube as small as possible to keep the costs as low as possible, right? And then you make the pod as large as possible. So what happens in the end is the remaining air in there, once you reach a certain speed, well, it still has to pass around your pod, around your vehicle, and at a given ratio, right? You hit a part where the air around your pod reaches the sound of speed, and you hit a limit where you can't really go any faster. That's where the compressor in the front is that takes that remaining air and sucks it in and pushes it out to the back of the pod. And in his very study, he used it also to levitate the pod via the air bearings, to take the air, compress it, and levitate the pod with it. However, so that's the very study of the Hyperloop. That's the broad concept that raised everybody's interest out there. And there are a couple of companies, a couple of startups trying to make that Hyperloop idea very real. But SpaceX and Elon Musk didn't really pursue that plan anymore, right? He said, okay, I'm busy with building rockets, I'm busy with building cars. Let's just make a student competition out of it. So what they did is they planned a big tube, and that's what you can see right here. It's about 2 meters in diameter. It's 1.2 kilometers long, and it's right next to the headquarters of SpaceX. And it's actually built, as you can see, just on the road, next to the headquarters. So the student competition was proposed, and there were two colleagues last year, Mariana and Diana, who talked about our steps with applying the competition, going to the design event, winning the design event, then going on further to the actual competition, and how we ended up there. So today I'm going to talk mostly about the competition itself, quickly about our pod, quickly about how we built it, about testing going on, and then how the competition went for us and what we learned from the competition. The tube, as already mentioned, you can see a cross-section over there. That's about 1.8 meters in diameter. And there's also an optional pusher vehicle that's provided by SpaceX for propulsion. So they want to make the student competition relatively simple because there's a lot of things going on. You have a vacuum tube, you have a system in vacuum that needs to work. You have to build a car that needs to work autonomous because, well, you can't control it inside the vacuum tube physically. So for propulsion, they said, well, we will build something like a Tesla that can push your pod initially, and then you can go on and fly autonomously and then brake by yourself. So last year, that's our team from last year, right next to the Falcon rocket that they have in the headquarters there. All the guys looking happy. And all of us together, we built the pod that looks somewhat, or basically like that. That's a rendering. We stayed similar to the initial idea in that we left in the compressor. We really wanted to have the compressor in as a kind of a scalability reason. We wanted to see how a compressor behaves in vacuum, what challenges there are next to it, and how it will work out in the end. Because you need the compressor if you want to make a cost-effective tube with a small diameter and a big pod. And then we decided to go with magnetic levitation and certain braking concepts, which I'll go into detail next. So you see in the very front the compressor that has the inlet and the fan in the very front, right? So the driving direction is to your left. And pushes it out the air through the very back, through the air duct, which goes just around here and to the end. We did decide on using magnetic levitation, so passive magnetic levitation, just by using permanent magnets. Once you reach a certain speed, you start levitating. And to reach that speed, we used wheels. So you have the big wheels, the big 4 wheels on each side, and a proper suspension with the wheels. We have 2 different braking concepts, which we'll go into detail, friction brakings and contactless eddy current brakes. And of course, you need power for the compressor, so we have 2 battery compartments and for our electronic systems and the computer stuff. Excuse me. No, there it goes now. So the compressor, there were different ideas for the compressor, and eventually the guys settled on choosing and buying off a compressor that already exists. It's part from the Alpha jet that was built in the 60s, I believe, from the French and the Germans. It's the first 2 stages of the fan they took out. They bought it off the Bundeswehr, actually, and put it in there. So that was quite fun. And the compressor is not like in a jet powered by kerosene or fuel. It's powered by an electric motor in our case. So behind the compressor, there's a very small and compact electric motor with about 30 kilowatts of power. And the whole motor is cooled with water capacitively in order to prevent an overheat, because especially in the vacuum, there's not a lot of air dissipation, heat transfer. Talking about the levitation, as already mentioned, we used permanent magnets. That's probably the simplest approach. The problem with air bearings that we talked about is you need really small and tolerances to maintain an air bearing. So you use a lot of pressure to levitate your pod off, but then the surface needs to be super flat, and that was not really given for us in the tube. So we decided on a more suitable system, which is magnets. And with magnets, permanent magnets, once you move a magnet over a conductor, you induce an eddy current that produces a repulsive force and then levitates off your pod. So in that case, our plan is is to get to a certain speed, and and with the speed, the levitation force increases, and we eventually start lifting off. And in our pod, as we planned it, I think the levitation, like let's say it's called the lift-off speed, was at around 150 kilometers per hour. So that was our goal: reach 150 and then go on levitating. Braking, there are two different brakes in there. First of all, there's the friction brake. It's like a brake caliper, as you know from your car, for example. It is pneumatically activated, but it's pneumatically vented and spring actuated, so it's absolutely fail-safe. So if we lose power or if we lose air pressure, the springs push the brakes together and we come to a stop. For high-speed braking, the idea was to use a non-contact way of braking, right, with very low wear, essentially no wear, because you have no contact. And there was electrodynamic eddy current brakes. It's just an array of 32 coils around each side that take a current of, like that produce take power of about 50 kilowatts and create a big magnetic field that induces eddy currents and then again breaks you, right? Eddy current brakes are not popular, so the whole system was designed by ourselves with the help of Knorr Bremse, our sponsor. There was a guy there who helped us a lot with simulations and laying out the design, and then the coils were made with another sponsor and built together. And that was like a one-off, basically, idea to see how it works out, because there's not a lot of experience with building eddy current brakes. The only eddy current brake in commercial use, I think, is in the ICE3. And in there, it's also only used on certain tracks that allow its use, because it heats up the rail, and then again, they need to get a certification for every rail. Computers, of course, there are computers that need to control the pod, to control the brakes, the, compressor and everything else, talk to the ground station, control the state machine of the pod. So we decided on just microcontrollers, our custom PCBs that we made. We had about 4 microcontrollers, each taking care of their own subsystem, talking together via CAN, and then relaying all the information out via Ethernet and the tube network that they installed, SpaceX, out to the ground station. So there was inside the tube, there was essentially a line feeder, sorry if you call it that way, essentially a leak cable that used as an antenna, and that allowed us to use 900 megahertz out to the outside of the tube, all along the track of the tube. And it worked reasonably well. Energy supply, of course, you need power, as already mentioned. We talked about 30 kilowatts for the motor, 50 kilowatts for the brakes. So we designed our own lithium-ion battery system, our own battery management system for that, and all of that had to fit into a vacuum-tight container, because what happens with pouch cells in vacuum? Well, they probably expand and then they blow up, and then you have no batteries. With cylindrical lithium-ion cells, it's probably possible, but again, they are heavier a little bit in comparison to pouch cells. So we decided on building a box, and that worked out perfectly fine. Another thing about the box is, and about vacuum, is we are operating in the tube we planned at operating at 10 millibars of pressure, and at the very pressure. And at our voltage of about 500 volts, you get a very, very short, sparking gap or sparking distance. So if you have two conductors within 2 centimeters, they will spark over to each other. So that's a very large distance. And keeping everything inside the box, you have normal atmospheric pressure in there. You don't have that trouble. You only have the trouble with the motor outside, but that was properly dealt with. Yeah, so that was kind of the overview of our pod. Everything had to be built. We built it in the makerspace in Garching. We had lots of contacts with manufacturers, get the stuff done, build it together. And once everything was built, or at least subsystems started to finish off, right? I mean, you don't just build the whole pod together and then test it somewhere, because we have no vacuum tube. We can't put it out on the road and drive it somewhere. That just doesn't work. And you have not the conditions you want to test. So what we really had to do is take every subsystem by itself or combine it in a reasonable manner and test it to what we want to test, what's reasonable to test. So for our brakes, for example, we went to a professional brake testing stand, designed our own braking disc, and tested it there to measure the braking moment. And that went reasonably well. We tested both the eddy current and the friction brakes. We had a levitation test stand, so the guys can actually experimentally determine the lift force and the drag force produced by the magnets when levitating, because simulations aren't that easy. In our second team now, the guys started with simulations and then experimentally verified that, and simulations really are not easy. Then, of course, sensors need to be tested. Sensors need to work at the speeds that we're working with. We are talking about, our design speed was always 100 meters per second or slowly below, so about 350 kilometers per hour. So you want to have sensors that can, for example, detect your distance inside the tube. You can use the levitation test stand or anything else to test the sensors properly. Everything you want to have in the pod, and that's critical in some way, needs to be vacuum tested, right? If you're talking about pneumatics, you already have a relative pressure difference, so usually pneumatics work well, but sensors work differently because usually they're relative. So you may want to test them in vacuum. You want to test electronics in vacuum. If you have high power electronics, then you have high heat dissipation and you have no airflow in vacuum, so that might be a problem. In our case, with small microcontrollers, if you stay below 2 watts or something like that, you'll be absolutely fine. But if you go in, for example, the motor itself, that needs to be water cooled, there you go and walk into problems, or the eddy current brakes that heat up, that may be a problem. And then again, the compressor that's in the very front that also wanted to be vacuum tested because, well, the compressor creates some air pressure and that's totally different in vacuum. And as you experienced, there was definitely a big difference than what we expected to be. To be fair, there was an issue with the blades somehow extending, so we eventually run at a little bit lower rotational speed that we initially planned on. But that's good that we tested it because, yeah, otherwise we would have found out in LA when it's too late. Organizing all of the testing is sometimes easy, sometimes difficult. For a compressor, we needed to find a vacuum chamber that's big enough. We fortunately found one of our a company called Steigerwald that does electron beam welding, and they do it in vacuum. So they have big vacuum chambers, and we went there. It was very fortunate that we found them, and we could test in there our compressor. Also, the batteries need to be tested for load, for discharge, and the battery box needs to be pressure-proof, right? Cannot leak. Yeah. So once we've finished all the testing, basically, and assembled our pod as far as possible, I mean, everything happened under time pressure because we essentially had about the competition was delayed, but we still had essentially about 6 months or so from planning and design to actually building a pod. And we started off from scratch. We had nothing in the front, so there was lots of things to do and to check out, and especially with testing and things you get back and you integrate back into your design. You design things differently, you manufacture differently. So there was a lot to do. Eventually, in January this year, we did fly over. Our pod was already on its way, and there's a short video I would like to show that just gives you an introduction when we fly over and go into our workshop we had set up in LA 1 week before the testing week of the competition began to just check the pod, do the last things we had to do, test it, and then set up. All right. So I gave you a small introduction. It was our whole week in LA, the first week. We spent at our workshop. As you saw, we basically took the pod apart almost. Well, didn't take it apart. We tested everything in there, did the last things we had to do, verified things. You saw lots of work going on there still. But we were lucky that in the end of that 1 week, we had everything as far as we needed it to for the testing week. So eventually, on the Sunday, we moved our pod over. We went to the testing lot on Monday, and it rained totally on Monday, so we couldn't do a lot. But on Tuesday, again, this Californian sun came out, and Christoph from TNG supported us very well with foods and drinks. He was there. There was a barbecue generously sponsored there, and a barbecue chef cooking for us. So, yeah, while most of the people, some of the people could enjoy barbecue and a Coke there, the other people were working in the background, right? So the testing week went on for 6 days before the actual competition. What the testing week involved is you present SpaceX your pod, you show them, it's similar to Formula Student, you need to show that every system works. It works in pressure, so there are different stages. We first go into a vacuum chamber to show your system works, and you go into a small subject to show that your sensors actually work, that you can be pushed, that you can brake. Eventually, you go into the tube without vacuum and get pushed at around 30 kilometers an hour, maybe 50 kilometers an hour, show that all your systems perform well in there. You do some fit checks, show them that everything works, that you do not touch the rail, etc. Before eventually doing the vacuum run and test on the competition day on Sunday. And again, to give you a small introduction to that testing week and how it went for us, there's another small video for us. So there's lots of things going on in testing week. You see all the other teams in the testing lot all preparing their pods, doing their safety checks and so on. It's an absolute pleasure to work in that atmosphere. You have all these different pods, all these different designs. You have all these motivated people building something, and it all looks fun and you know, a lot of fun. But it's also a lot of work. So we woke up every day in the morning, went there, stayed until the very late, until we had to leave, and then the next morning be there at the earliest time possible again, and then leave in the night again, just to get through all of the testing. And there was always something to do. So there was lots of things to do. And in this 1 week of just proving that your pod works, there was very tightly scheduled. So there are a few things that we learned during that very testing week that we would like to share, at least for us and for us to keep on with the next team. Sorry. Okay. Got it. So one of the things is, for example, shipping. Shipping is a big deal, and customs can be a big pain. I don't know, any of you have dealt with export and doing carnets and customs and so on. There's a lot of planning and a lot of paperwork going in the end it still doesn't work out, right? So what happened with us, we shipped our batteries and our magnets earlier on because they're dangerous goods. They were shipped via ship, and then the pod flew in via plane. However, we arrived, the ship left 1 week later. It was delayed in Germany. It was delayed for 1 week in America. But it was still on time. But when we got there, we got the notice that customs pulled out our container for a deep inspection search. And we eventually got our magnets and our batteries like 3 days before the competition, delivered to us with the beautiful examined seal here from the customs office. So that was a big deal breaker. However, there was still a good thing. We had more batteries on hold in Germany. We bought them in double the amount that we needed in. So all the other team members who weren't there for the very first testing week, everybody took 2 batteries with them on the airplane in their hand luggage, which is allowed by the airline. You can carry 2 batteries up to 100 watt-hours on the airline as your carry-on inside a safety bag. And so everybody took 2, and then we had enough batteries over there. And eventually, once the customs batteries arrived, we had more than we needed, right? That's just one of the things that can go wrong, right? We didn't expect it. We planned it way ahead, but it still didn't work out. I guess this year we're going to take them with a carry-on straight away. Let's see. Other things can work out. We had a motor controller, for example, for a low-speed propulsion system. And during the first testing or like the second testing period, I mean, it always performed beautifully, but during the second testing week, then it started, going slowly, and eventually, didn't do anything anymore. Well, you see here the few resistors, the kind of shunt that just blew out, and the whole motor controller was gone. Any system you tested, anything else you have, it can always fail, right? So be prepared that your system can fail. Be prepared to have backup. If you don't have backup, know that you can buy it somewhere else. So in our case, for the backup controller, we went to Anaheim and brought 4 new motor controllers there, put them in, and they worked. So we're happy about that. Testing itself, it's the same story every time. If you do it here in the test setup somewhere, you set up your tests, you planned well ahead, right? You set up your tests, but in the end, you still take 6 more hours because some cabling doesn't work or something else doesn't work out. Testing just always takes longer than you want it to, and it always takes longer than expected. And the same story was true in the testing lot at SpaceX. All the tests were planned by SpaceX, but lifting the pod to there and lifting it on the tube, well, it maybe takes 1 hour longer than expected because our pod is heavy and it's hard to maneuver. Then maybe their pusher didn't perform as well, or their pusher had a problem, so they needed 2 hours to fix the problem with their pusher, right? And eventually you stand there on the rail for 4 hours, waiting for the pusher, maybe fixing your issues before eventually starting. And once you're done, the next team can go on, right? So in our case, there was always the aim to be the first one in the testing, to finish the checks the very first, because otherwise, well, if the other teams have problems, you are back in the waiting list and you have to wait for them to finish, right? Be on top of your game, be prepared, always do your tests the very first and plan them to be longer, take longer, and stay the night as long as possible if you have the chance to, if they let you, right? It doesn't matter what happens. Yeah, so eventually on Sunday, after all the testing, we did move into the competition day. There were 3 teams scheduled for an actual vacuum run. That was MIT in the morning, that was us in the afternoon, and then Delft after us. All the other teams didn't get through the testing, all of the testing. There was another 1 or 2 teams after the event who still did an open air tube run. All the other teams didn't even get a chance to do a competition run. It was unfortunate for them because there were about 3-4 other teams who were prepared and ready. Other teams were not ready. However, it's the same deal. Try to do it as fast as possible and be prepared, right? So for the competition day, there's another video.
Here we go. 5, 4, 3, 2, 1. WARR is currently on their own power. All the way down the tube. And that completes WARR's successful run, and now we're going to depressurize.
Thanks. I don't know if you've seen it, and so basically the screen was built up here, and you had the different cameras within the tube. They weren't all in order, as you saw, the pods moving in from different directions. But you had the timeline in the very big middle, where you saw the pod moving. The blue part was our pod moving in, reported by our telemetry, and the speed that reported. And the white dot behind was the pusher that pushed us up to around 400 meters here. So as said, before us, they were Delft. After us, before us was MIT, after us was Delft. The runs are online to see. And they all, just to say, they all did a great job. Everybody did a great job. What we eventually did, what our difference was to all the other teams, if we actually moved till the end of the tube. What was the issue there? I don't know. The other teams, they got pushed with the pusher with the same profile up to, let's say, 400 meters. But they stopped at 500. Okay. Why did we move to the end of the tube? So in that case, we won the fastest pod because, well, we moved to the end of the tube, right? The pusher vehicle that you can see here from SpaceX that was built, it's essentially like a Tesla. It has motorcycle wheels and suspension there and batteries here and 2 Tesla motors in the front and back to push you. It didn't perform as well as expected. They told us they can do 2 Gs of acceleration and 300 kilometers an hour at least. That didn't work out. We eventually were pushed up to only 90 kilometers per hour. That was partially due to the problems being in testing. So due to delays with the pusher in testing, we only tested up to 50 kilometers in open air and then went to 90 kilometers per hour in vacuum, right? I guess they wouldn't ever let us want to test up to like 200 kilometers per hour immediately in vacuum. Maybe there was a different issue with the pusher. We don't know. Let's see how it works out this time. So what essentially happens, we talked about lifting. There's a certain point at where you start to lift off. And there's not only the lifting force, there's also the drag force. And the drag force has a very sharp peak at the low speed and then eventually decays off. And that 90 kilometers per hour was also for the other teams and essentially us, always the point where the drag was the highest. So the magnets that lift you up and give you, frictionless levitation, they also produce drag and then slow you down. So the other teams, they moved up, levitated up to that point, but they had a huge drag in there. So once the pusher stopped pushing them, they essentially, it was like a full break they had, right? It would have been the same for us if we wouldn't have unmounted our magnets for the run. As simple as that. We just took them off because there was no use case for levitating in that very moment with 90 kilometers per hour. And that's thankfully part of our design that kept flexible. We had aluminum profiles as the structure. So everything in there was screwed on, mounted on, and you could take off at any time, more or less, right? So at the testing day, we took them off and we run until the end. So you don't know if there are factors in your design, if in your competition, whatever, that you can't influence, right? Be prepared they don't work out. Be prepared things do not work out, and that you may have to adapt your design to it. Yeah, so that was in the evening after Delft finished their run finally. The celebration, Delft won the main award for best overall engineering. We won the main award for the fastest pod. And then there were sub-awards awarded to most other teams. And then we had a party with Delft afterwards in a pub, so that was fun. What's next up, right? At the very day that we were there at the competition, Musk came in for a speech, then he left, and he watched our run, and he left. But at the speech he said, well, we just started digging a tunnel, and I'm thinking of starting a tunnel boring company, right? So we're like, what? Okay. And at this very parking lot that's next to the main entrance, so you have the main entrance, the road, and then this parking lot, we parked on there on Sunday to do our safety briefing. Next Sunday, there was a hole in there and diggers, and they were starting digging a hole there for his boring machine, right? So let's see what comes out of the boring company. Maybe there'll be a new competition in a tunnel next time. Let's see. That was at least very fun. What we do know, however, is in August there's the next competition, the second competition. And what SpaceX is planning to do is make it a yearly competition, very similar to Formula Student. In the next competition there will be not 2 main awards, there will be only 1 main award, which will be fastest pod. So we will again try to be the fastest this time and learn from our lessons that we had. And be as light and fast as possible. There's a new team forming, well, it's not forming, it's already formed, and we are hard building stuff. And there's lots of things going on because until August we have to finish our pod, so I have to take off early today again and go there and work. Not study, but work for the projects, of course. And the vehicle will be shown in July. I would love to tell you more about it, but we decided on keeping it secret until July. It will look very different than our old pod. Yeah, so thank you. Thanks to all our sponsors. These are the sponsors from the second team. Thanks TNG for both sponsoring the first and the second team. Thanks to all of you guys for coming here and to listening and for your interest in the topic. And if you have any questions, I'm very happy to answer them.
Yes, thank you, Martin, very much. Very interesting talks. So we have at least 10 minutes for questions. So if anyone has a question, I hope so. Go ahead.
Okay.
Really? No questions? Okay. Then, there's one.
The next run, do you try to levitate?
Let's see. July isn't far away. Yeah, I mean, we talked about the problems we had, and so there are different. Well, you can figure it out for yourself. If you go 90 kilometers per hour, it doesn't make sense. If you go 300, maybe it does. Wait until July, and you can find out. If you're more interested in that, look into. There should be at least some papers online for electrodynamic levitation with permanent magnets. You can find the mentioned figures there with the peak drag and so on. So that's interesting to know, actually, and to look into.
So as I remember, you were only team using the compressor. How did it work out? So was it a good idea, or will you keep it for the next round?
Yeah, that's true. The only team with a compressor. nobody else tried it, simply because it wasn't necessary for the competition. Because we mentioned that the pod needs to, if you want to make the pod big in comparison to the tube, then it's critical at very high speeds, right? That wasn't the case for us. We've always planned with 300 kilometers an hour. The tube had 1.8 meters in diameter. Our pod was about 1 meter wide. So for us, it wasn't an issue. We didn't have to use the compressor. However, we wanted to use it as a key selling point, basically, and to look into what happens with a compressor. That was very interesting, right? Nobody ever took a compressor and operated it at that pressure yet. So that's a thing we wanted to see. That's the thing that got Airbus interested as our main sponsor, of course. And so it was just basically testing it out and seeing how it works out. We figured out there were some problems. It did not work as planned directly. We still used it in the competition, and you saw it maybe in the video with lots of dust coming out at the end. It was partially through the wheels because the rail was dusty, but in the end you definitely see a big dust cloud from the compressor itself. We ran it at half speed. That was what worked out for us in this case. If you want to go full speed or maybe design your own compressor, make reasonable changes, there would be things to investigate in there that weren't so trivial that we saw in testing.
So you said that the pod was pretty heavy. How heavy was it?
550 kilograms, I think, around. It comes, I don't know, for example, the eddy current brakes, they were at least 50 kilograms because it's just coils and iron. You have compressor, 60, 80 kilograms. The structure, the brakes, it all adds up to about 500 kilograms that we had in the end. There was still, in the very front, there was a seat. We put in like a bicycle seat, so there was space for one human. Of course, there was no human in there because we didn't have a pressure cell. But there was supposed to go a dummy on there during the test run.
So was the speed you achieved roughly the speed you wanted to achieve?
No, it was 1/3 of the speed we wanted to achieve, or actually a little bit less.
But you removed the lift-off system, right?
Exactly.
Before you started, right?
Yeah, we removed the magnets for lifting, right? Otherwise, we would have just stopped immediately after those 90 kilometers per hour. The point is the pusher pushes us to a certain speed, and maybe that gets confusing. The compressor is not for propulsion. It doesn't it doesn't move us forward, right? It just sucks in the air like a big fan, like a hair fan, right? It blows out air in the end, but it doesn't move you forward. Like it doesn't compress the air and then pushes it out. It doesn't make it hot like a compressor in an airplane. It's just for removing the air. So once we are pushed to a certain speed, there was no way of accelerating any further. So that's the whole idea in there. And that was the case for every team. As far as I know, I don't think there was any other team with onboard propulsion to go faster than the pusher would have pushed them. Yeah.
And one more question. So what was the degree of vacuum in the tube?
Sorry?
What was the degree of vacuum in the tube?
It was about, in the end, it was 100 millibars, so it would be 1/10 atmospheric pressure. Specification was 10 millibars, so 1/100th of an atmosphere. But the tube, the vacuum pumps or the tube didn't perform as specified in that case.
So maybe not relevant to the competition, but as to the concept of the Hyperloop in general, have you heard any discussion of the practicality and maybe the cost of maintaining vacuum in such a large, full-scale, long expanse of tube?
That's a good question, but I'm not too sure. I didn't, do any calculations in that regard. I think it's reasonable. For example, for that 1.2 kilometer stretch we had there were 6 big vacuum pumps there with a big generator in there. So yes, there's some need, but if your tube is actually tight, then the pumps don't have to work as much, right? If you keep in airlocks and so on, then I think that all works out reasonably well. The other idea that was also proposed in the alpha study, of course, was to put solar panels on top of the tube and essentially produce more power than you would ever need to maintain a vacuum. So I think that's solvable. Also thermal expansion that people always criticize, the tube will expand, that's also solvable. The only real issue I see with building a Hyperloop or a rail is the rail itself, because, you know how much trouble it is if you want to plan a power line in Germany. People react to that. If you want to build a new rail somewhere, that's not easy. Maintaining a real rail as in costs, that's also costs some money, right? So that's I think the biggest challenge. To find some land, build a rail, plan a rail. That's always what hinders that plans the most. Essentially, you go like as Deutsche Bahn. They're just maintaining their tracks or improving them, but they're not expanding their tracks, right? And essentially, you go there and say, well, I'm going to build a new highway or a new rail. So that's a big deal and a big challenge to face. And in my eyes, the biggest one.
I have two more questions. The first one is next challenge. There are only the 3 teams that managed to solve the last challenge, or are there more teams again?
We will find out, essentially. The plan from SpaceX side is to do it just the same way as last year. So 1 week of one testing week, and then 1 day of competition. Would be nice to have 2 weeks, of course, then more teams can finish in time. But maybe they are more prepared this time from their side because last time, for example, with the pusher, they still had issues, so they fixed them by now, I think, in the competition. So it should work. It should just work, right? So then there may be less delays. Maybe the teams are more prepared. There are some returning teams, some new teams. Maybe they're more prepared with procedures of moving onto the rail and off the tube and so on. That could shorten the times. So we'll see. But as mentioned, there are teams that had the chance to go in there, and there are teams that did not have the chance, that basically started to assemble their pod in the parking lot. So it's always, and with student teams, I mean, everybody put in a lot of effort, so I don't want to discredit anybody. But it's just, it's a matter of planning, lots of discipline, and keeping there and staying there. And I mean, everybody does it in their free time, everybody works in there for their free time, but you need people who basically do it as a full-time job and put in the effort to get it from, planning to actually building, testing, and working, right? And when students are leaving, that's a problem. When students are only doing part-time or whatever, then that's a problem. So there are lots of factors in a team that affect your performance in the end. And I think Formula students face that challenge probably every year, but I think they've figured out how they use it, or like how they organize their team pretty well over the years. And for us this year, it was always a new team, new structure, little experience. Delft, for example, I think there's a lot of guys from Formula student of their team who participate in the Hyperloop team, so they were also very well organized, and you noticed that. I mean, they had in the design weekend, they had a CAD very well done, and yeah, so they were well prepared.
Okay. Do you know any other team that tried to use the air levitation system, or did all use the magnet?
No, they were both concepts. Basically, it was everything in the wheels, air bearings, and magnets. Air bearings were also there. There was a high school team actually participating who were super prepared and were well designed. They used their air bearings in the vacuum chamber, for example, in the static test, which went, I don't know, I think reasonably well. There was another team, Lehigh, who used it on the open air track, which we saw. They had problems, for example, because the sub-track, there's an aluminum rail in the middle and then aluminum plates on the sides, and there are gaps between the aluminum plates, and they are, I think, like 5 millimeters large. And so once they moved over those gaps with the air bearings, they lost all the pressure and essentially collapsed on there, which then again wouldn't have worked in the tube because you have those gaps every 4 meters. Yeah, so there are challenges with air bearings which make them not attractive, but teams definitely use them.
You said that you don't know exactly what the next test would look like. Could you tell us what the main aim for you is in the next test?
The next competition, or?
Yes, next competition.
Be the fastest one, win the competition.
Anything that is different from the last competition? Yes,
as mentioned, the pod is definitely quite different from last year, but we would like to stick until July. Yeah.
Did the specifications for the next competitions change?
Not at all. Basically, the tube is built. They are not changing it as far as I know. So they didn't give us an update on any specifications. The testing is planned to be similar, so it's basically the same competition again. Just one criteria.
Okay, I think we have time for one more question before we have to go to the next presentations. So,
well, first, thanks a lot for the talk. Was the tube completely straight that you drove through, or have you put thought already into how to do turns and stuff like that?
Sorry, I didn't hear that.
Can you do turns in the tube, or is it completely straight?
It's completely straight. In our case,
on doing diversions, will this ever be possible?
Yeah, I mean it's always possible. We are fixed to the design given by SpaceX of the tube. They told us we have an I-beam in the middle that we can work with, and the subtrack, and it's always flat. So we worked with that, of course. If there's a slow bend in the tube for big turn diameter, it would be fine. It would work out for us as well. If it's a very narrow turn, of course, then there might be issues, but it's the same as in a train. So essentially, that works out. If you want to go really high speed, then you would like to bend into the tube, right? You would like to bank in there, so you don't just push your vehicle. You would like to bank in there, and in that case, then of course the whole design of the tube may need to change. It wasn't in scope for this competition. But it's possible. Even with the current design, you could bank it on the side. That would be possible. But for now, that was a hard enough challenge to just get something in there and get it to stop, more or less. Yeah.
Okay, then. Thank you very much for the presentation.
Thank you, guys.